Greetings everyone, this is Professor Roman. Let's continue the group theory lectures. I want to talk now about subgroups of a group. We'll go over this briefly so that we can use this concept, and at a later time we'll take a closer look. Begin with the definition. Let G be a group, a non-empty subset. H of G is a subgroup of G. And I'll denote that using a less than or equal to sign, but I would not read this H less than or equal to G. I would read it H as a subgroup of G. If the restrictions of the three group operations on G to the subset H define a group structure on H. As to some notation, if H is a subgroup of G but it's not all of G, then we'll write this. We'll use a strictly less than sign, and H is said to be a proper subgroup of G. A group is a subgroup of itself, pretty trivially from the definition. It's the only non-proper subgroup. This notation I'm going to use as a shorthand for saying that each of these subsets is a subgroup of G. And finally, we'll denote the family of all subgroups of G by sub G. Later on, we're going to see that sub G has its own algebraic structure. It's a complete lattice, but that will come later. So the question then becomes, what does it take for the restrictions of the three group operations on G to actually define a group structure on H? Well, we discussed this when we talked about widgets and discussed it in general terms. It means that the restrictions of the operations are actually operations on the subset. And that, well, in this case, the group properties hold for the restricted operations. But as we also discussed briefly, if the restrictions are indeed operations on the subset H, the group properties will follow. They will hold. The point is that the restricted product is really the same product. It's just that it applies only to the elements of H. So since the product on G is associative, it's still going to be associative when restricted to H. And since the identity element 1 belongs to H, that's what it means to say the restriction of the identity element on G is an operation on H, it's also the identity for the product, for the product on H, the restricted product. And since the inverse of every element of H is in H, it's the inverse under the restricted product as well. The fact that we're restricting, in a sense, has nothing to do with the properties. So we only need to check that the restrictions of the operations on G are legal operations on H, or put another way, as again we have discussed, we only need to confirm the closure of H under the three operations on G. And here is the definition of closure, which I gave you once before, but this is in the context of groups now, not widgets. Let G be a group and let H be a non-empty subset of G. H is closed under the product on G if the product of two elements of H belongs to H. And we also say that H inherits the group product from G. H is closed under inverses if the inverse of any element of H belongs to H, And so in that case, we say that H inherits inverses from G. And finally, H is closed under the identity element of G if that element belongs to H. And again, we say H inherits the identity element of G. Some of this language may seem a little overblown, but it's there for consistency. Certainly the first definition here is not overblown. You may consider these two a little bit more wordy than necessary, but we want this consistency throughout. So the closure of H under the three operations guarantees that H is a subgroup because the group properties follow. But it's enough that H be closed under products and inverses to guarantee that it is closed under the identity. And the reason is that, well, certainly if H is the trivial group, that is the case. It doesn't make any difference. If you take an element H in capital H, any element, its inverse is also in H if H is closed under inverses. And since H is closed under products, H inverse belongs to capital H. Well, that is the identity. So closure under product and inverses is sufficient to guarantee that H is a group under the restricted operations of G. But if H is a finite non-empty subset of G, we can do even better. Closure under products alone is enough. It will guarantee closure under both identity and inverses and therefore give us a subgroup. This is certainly true for the trivial subset. If it's closed under, it is closed under product, it's closed under inverses, it's closed under identity, so it's a subgroup. So we don't have to worry about the trivial case. If H isn't trivial, then what we can do, this is a technique that is worth absorbing because it's used in other contexts. This is what we can do. We can grab a non-identity element, A sub k of H. Here's H, it's A1 through AN. So grab any fixed non-identity element of K and multiply through. Multiply each element of H by H sub K, A sub K. So we'll get this list of symbols. These all belong to H. They're distinct because of cancellation. So they do, in fact, constitute H. So just to summarize, you can multiply any element, you can multiply all the elements in H by any element of H, and you just permute the elements. You still get the full set H. Well, one of these has to be A sub k. A sub k is in H, so it's got to be one of these products. So there's an index I for which AKAI is AK. And that implies that AI has to be 1. And there's a sentence of justification that's required for that. I left it out because I want you to fill it in. Don't jump to any hasty conclusions when you do that. Be careful. But it is just one sentence. So H does inherit the identity of G. So closure under products for the finite set does imply closure under the identity. As to inverses, for convenience, let's just say that A1 is the identity. One of these is the identity. We'll say it's A1. The common phrase for what I like to say for convenience is without loss of generality, but I really dislike that phrase, so I stay away from it. And I especially hate the abbreviation WLOG, which students like to use. I would stay away from that. In any case, so this is what H looks like now, because A1 is the identity, so this is just AK here. But one of these elements, other than AK, has to be the identity. The identity is in here. We just proved that H inherits the identity. AK is not the identity. We deliberately chose it to be a non-identity element. So one of these others is the identity. So let's say AKAJ is the identity. Well, that implies that AK inverse is AJ. And again, another sentence might be helpful here, and I'll let you formulate that. So H also inherits inverses. Question for you, do I need to check not only that AKAJ is 1, but also the reverse, AJAK is 1? We're not dealing with abelian groups here. Why didn't I check this? Did I miss something? Or is it unnecessary? So in summary then, if H is a non-empty subset of group G, H is a subgroup of G if and only if H is closed under products and inverses, because then it will also be closed under identity. If H is finite, H is a subgroup of G if and only if H is closed under product. And I will add another comment here that I didn't put in the book. You might see, especially in a book on finite groups, as the definition of subgroup that H is a subgroup of G if it is closed under products. I really don't like that definition. It's not in the spirit of the concept of a substructure. Our definition that the restrictions of all of the structure forms a structure on the smaller, the subset. That is the true spirit of substructure. This, therefore, should not be the definition, in my opinion, although this is the more practical approach to showing that a subset is, in fact, a subgroup. There's no point, after you've shown that it's closed under products, that you show that it's closed under inverses or identity, because that follows, unless there's some reason you wish to. Okay. So I'm only taking exception to style here and what should be considered the definition, but it's really a little more than style. It's really the spirit of the whole subject of substructure. Let's look at some examples. G is a non-proper subgroup of itself. This subset containing the identity is a subgroup of any group. It's called the trivial subgroup. Z is a subgroup of Q, and that statement is a little lacking too. I don't see any operations mentioned here. So are we talking about multiplication or addition? Well, I'll let you sort that issue out. Or maybe I shouldn't. Q is a group under addition, but not under multiplication, because 0 doesn't have a multiplicative inverse. So there's really no choice here. You will see this a lot. I said before you should always mention the group operation, at least the binary operation, the product or sum. But frankly, many authors do not always do that. Okay. As a student, I would strongly recommend you always do that. but we all get older and get sloppier, and it is a bit sloppy. But it doesn't really do any serious harm when there's no choice as to what the interpretation has to be. How about Zn? This, if you recall, are the integers from 0 to n minus 1 under addition mod n. This is not a subgroup of Z. It is a subset of Z, and it is a group under it, but not under ordinary addition of integers. It's a group under addition modulo n, so it's a different operation. It's not a group under the restriction of addition to Z, to Zn, because if you add two elements of Zn, it's not necessarily going to be in Zn if you don't reduce mod n. Okay. The set R plus, I'll let this be the set of all positive real numbers, let R minus be the set of all negative real numbers. Both of these are, of course, subsets of the non-zero real numbers. And this is a group under multiplication. R plus is a subgroup, but R minus is not. The general linear group, GLN of R, of all n by n real matrices is a subgroup of the general linear group, GLNC, of all n by n complex matrices. And this is a multiplicative group. Now, these are invertible matrices. The sum of two invertible matrices is not necessarily invertible. That's not an operation on this set. Multiplication is. Okay. The special linear group, SLN of R, is a subgroup of the general linear group, GLN of R. In a cyclic group generated by an element A, the set E of all even powers of A is a subgroup. In fact, generated by A squared. So you should ask yourself about the set of all odd powers. Is that a subgroup or not? As we have discussed, if G is a group and A is any element, then this set doesn't look like it's centered here. I better check that. This is the set of all powers of A. This is a group under the product of G. We discussed that at length. It's the cyclic subgroup generated by A. And its order is equal to the order of the generator. The dihedral groups, we discussed D8, the symmetries of a square in particular. They are subgroups of the Euclidean group, the group of all distance-preserving maps of the plane. The quaternion group Q8 is a subgroup of the general linear group, GL2 of C. So those are some basic examples. One more thing I want to mention about subgroups before we move on is a matter of terminology. Although it's not standard terminology, I want to introduce a term that will be very useful for us. Frankly, I'm surprised there is no term that's universally accepted for this. Maybe there is and I missed it, but I don't think so. But the reason for introducing this term is that it's not possible for two subgroups, H and K of a group, to be disjoint, because they both have to contain the identity element. So the closest that we can come to disjointness among subgroups is that their intersection is trivial. And that deserves a name. two subgroups H and K of a group G are essentially disjoint if their intersection is trivial. So this is my terminology. You may not see it elsewhere. Others may not understand it until you explain it, but it's pretty simple and rather obvious, I think. We'll denote the set product of two essentially disjoint subgroups with a heavy dot. So when I write this, it means that G is the product HK. Remember, this is the set of all little teeny products of an element of H times an element of K, and that H and K are essentially disjoint. We're going to have a lot to say about this situation. It is a true decomposition of G into a product of subgroups. Because these are essentially disjoint, there's no real interaction between the two, and we get a legitimate decomposition of G into, well, dare I say it, simpler groups. They're not necessarily simpler, but they may be. So we'll discuss that at length. An important example of a subgroup for any group is the center of a group. And the situation here is, even in a non-abelian group, some non-identity elements might commute with everything in the group. That's certainly possible. These are rather well-behaved elements. Those elements, together with the identity element, form a very important subgroup of any group. It might be the trivial subgroup, but it often is not. The center, denoted by Z of G of a group G, is the set of all elements of G that commute with all elements of G, or with every element of G. So it looks like this. Z of G is the set of all A and G, such that AX equals XA for all X in G. A group is centerless if its center is trivial. So be careful there. Centerless would seem to mean that the center is empty, doesn't exist. But the identity element is always in the center. So again, this is, maybe it should have been essentially centerless, but it's not. This is the term centerless. And I'm going to leave it for you to prove that the center of a group inherits products and inverses, and so is a subgroup of G. As one example, if you look at the quaternion matrix group, it's these 8 matrices here, the positive and negative, each of these. Since AB is not equal to BA, and since AC is not equal to CA, A, B, and C cannot be in the center. Neither can their negatives. That only leaves plus and minus the identity. The identity is in the center, but so is negative I. That's easy to check. So the center of the quaternion matrix group consists of these 2 matrices.